we will pretend. So let's assume that this is 1.5 meters this way and 2.5 meters this way. Matter of fact, I'm going to change that into numbers that I can multiply more easily. We'll make it a 2 by 3. What is the area vector for this surface? If it makes life simpler, let's go ahead and define I hat to the right, j hat up, and therefore k hat coming out the board. Are you stopping? Giving someone else an opportunity to finish it? Okay.
K hat.
Or, what's the other correct answer? Yes. It is a vector, there is a direction, there is a magnitude. We got the magnitude, Sarah supplied that, and then the k hat or negative k hat, Daniel or Olivia. Just because it's a two-dimensional surface, it's not, surfaces by definition are two-dimensional. It is an open surface, so that means my vector is either pointing this way or the other way. If it's a closed surface, like my sphere is, sorry, eyelash. If it is a closed surface, then my area vector's got to be pointing outwards and perpendicular to the surface. So if I'm right here, well, let's go for, the stunning visual effects. So if I'm here, my area vector is going to be pointing outwards. So that would be my area vector in blue here. Here is pointing in that direction. Here is pointing in that direction. There's pointing in that direction. Here it's that direction. There's that direction, and so forth. My area vector is pointing just straight away from the center because this is at the center. So if I did a dot product, E dot A, let's flash back to what dot products are. What is a dot product? As opposed to a cross product?
You're multiplying vectors.
Okay, same with a cross product. All right, so multiplying vector. So my electric field is K Q over R squared R hat. My area vector is, what is the area of a sphere? Surface area of a sphere?
2 pi r.
That's the circumference of a circle. So 4 pi r squared. It's an area, so we're going to have two length dimensions, r hat. So if I just multiply these two things together, I get 4 pi k sub e q. But I still have this r hat dot r hat. Since bells do not seem to be rung right now, let's flash back to 151. Work is force times displacement. What can you tell me about a dot product? Torque is equal to R cross F. just give a contrast there. What's the big difference between a dot product and a cross product?
Units?
Pardon?
Units?
This would be Newton meters and that would be Newton meters.
The product of multiplication would be a vector,
With which multiplication?
with dot products,
That produces a vector?
with cross products.
That produces a vector?
Yeah.
Yes. This cross product here is called a cross product because there's a cross there, and this is called a dot product because there's a dot there. This is also known, not only is this a cross product, it's a vector product. And this right here is a dot product, also known as a scalar product. So when I do a dot product, I'm going to get a scalar. When I do a cross product, I will get a vector. Technically, it's a pseudo vector or axial vector, but that's beyond the scope of this course. This is also called an inner product, and this is called an outer product. All right, so it produces a scalar. When I'm multiplying, which one deals with parallel, which one deals with perpendicular? For one of these, I'm multiplying parallel components. For the other one, I'm multiplying perpendicular components. You got a 50-50 shot. I'm only willing to gamble that. Worst it comes off is that you're wrong. Or you say, of course the answer is, and then give an answer, and you might be right. No one take a chance. Which one cares about parallel?
Dot product?
Yes. When I'm trying to figure out the work done, I care about how much force is in the direction of movement. This is the parallel. This one's the perpendicular, and sort of a visual hint is the fact that those are sort of perpendicular. This multiplies perpendicular parts. That's why when you open a door, it is more effective if I apply a torque farther away perpendicular to the door than applying a force parallel to the door. If I apply a force parallel to the door, it doesn't really do a whole lot in theory, but it's much more effective to apply a force perpendicular to the door because I apply a better torque. All right, so if it cares about parallel, if I take some vector here A and some vector here B with some angle between them, if I'm doing a dot product of A dot B, I want to multiply parallel parts. So I break B up into components because I picked it. This piece right here is B cosine theta. This is B sine theta. So A dot B would be A times B cosine theta. Suppose I do A dot A. What would that be equal to?
One.
Not if you're stopping there. Sorry, the question to fit that answer is, if I do I hat dot I hat, what is that equal to?
1.
A dot A.
E squared?
How'd you get that?
It's multiplying by itself, so it would be squared. Just
Okay.
went mathematical.
Yeah. One way of looking at it is, I care about multiplying parallel parts. Well, A is completely parallel with itself. All of A is moving in the same direction as itself, so I'm just multiplying the parts that are parallel. Or in this formula right here, the angle between any vector and itself is 0. Cosine of 0 is 1, so it just becomes the product of the magnitudes. This is equal to 1 because their magnitudes of unit vectors is 1. What is I dot j?
0.
Yes. All right, so over here I took the coefficients and multiplied them together, but now I have this r hat dot r hat. What is that equal to?
1.
Yes. So this is my final answer. E dot A is equal to this. Now we're going to take this one step further and make it look like, put it into a simpler form. On the first day, when I gave you that the electric force, 1 on 2, is equal to KE Q1 Q2 over r squared, r2 hat. I did comment that there was another version of this formula introducing this thing known as permittivity. And so this formula right here, permittivity, which is an epsilon, or they're both called epsilon. So the electric force is equal to 1 over 4 pi epsilon sub naught Q1 Q2 over r squared. This coefficient right here is just the same thing as K, the electrostatic constant. So if 1 over 4 pi epsilon sub naught is just my electrostatic constant, what does epsilon sub naught equal? This is a math problem.
1 divided by 4 pi k.
Hey, I just happen to have a 4 pi k sub e right here. What a coincidence. So 4 pi k sub e would just be 1 over epsilon sub naught. So this just q over epsilon sub naught. Now we can generalize it by putting it in q over epsilon, just drop the subscript 0. I'm about to generalize it one more time. Questions up to here? This E dot A, that has a name. This is known as the electric flux. Capitalized for some reason, who knows? And that's E dot A. And that the electric flux through a closed surface equals the enclosed charge divided by epsilon. If free space epsilon is equal to epsilon sub naught, which is 8.8, approximately 8.85 times 10 to the 12 coulomb squared per Newton meter squared. So now, this is incredibly useful. If I start out with a sphere here and I have a 3 nanocoulomb charge sitting right there, what is the electric flux through this surface? Wrong symbol. Notice I dropped the required, this 3 nanocoulomb charge is not in the center. It's just somewhere inside my surface. Inside the sphere. My electric flux through that surface is, well, it's 3 nanocoulombs divided by 8.85 times 10 to the negative 12. So that's nanocoulombs, so let's just go ahead and change the nano to 10 to the negative 9 coulombs. And this is coulomb squared for Newton meter squared. So first off, oh, that's 10 to the positive 12, not negative 12. I wrote it correctly over there. So what's the numeric part of the answer? And then I'm going to ask you, what are the units?
.39 times 10 to the negative 22nd.
All right, and units? What are the units?
Is it joules?
It is not.
No. That's
Coulombs.
not
It is not a one word.
Newtons times meters per second over coulombs.
Where'd you get your second?
Oh, just newtons times meters. Or per
Wait.
coulomb.
That would actually be a volt. It is not volt. You're close. You left something off.
Meter squared.
Meter squared. And this is also the same as a voltmeter. Or meter volt, but voltmeter.
Is that negative 22?
Say it again?
Is that negative 22 or negative? I thought the times 10.
That is
That-
negative 22.
That's a negative 22.
Okay.
Yep, sorry. I heard 19 for some reason. Wow. Oh, yeah, we got time. Any questions to hear? Because we're about to exploit this. All right. Up till here, we have talked about electric flux almost exclusively about the electric flux, or sorry, electric field, the electric force from a single charge. We now can start dealing with something more sophisticated. So, let us start out with a sheet of charge. Infinite sheet of charge. Infinite sheet of charge. So this is sort of the jaunty tilt view or a side view. Side view. Jaunty tilt view. And I want to know, what is the electric field at this point right here, a distance r away? Now, when I say infinite sheet, from a pure math point of view, it has to be infinitely large. from a practical point of view, it just has to be large compared to to R. Generally, 10% rule, if the dimensions here are more than 10 times that distance right there, this is a decent approximation. So the first thing I'm going to do is create a Gaussian surface. It's an imaginary surface that basically it's going to be at that point, and then so it's a distance r on both sides. So imagine it's a sheet of paper, and see, these two are the same. So ignoring the hooks, this is basically the two masses that I have in my hands. Those are the Gaussian surface I'm talking about right there. It's like I have got a can on both sides of the paper. For the camera. As if you can see it in the shirt in the background. And now what I'm going to do is I am going to use this idea right here, this enclosed surface, so I'm just going to abbreviate it as CS, is equal to the enclosed charge over epsilon sub naught. I am going to say that this sheet right here has a uniform surface charge density. In other words, if I take, let's just say 1 square meter, no matter where that 1 square meter is, the enclosed charge is always the same. So I know that sigma is constant. I'll put a little subscript E there. I'll usually drop the E because we're talking about electric stuff anyway, but constant. This is the surface charge density.